All right, welcome to Chapter 7 from Introduction to Oceanography. Today we are talking about atmospheric circulations, and the main concepts for Chapter 7. First, the Earth's ocean and atmosphere are unevenly heated by the sun. So what does that uneven heating do? It essentially moves mass north and south to compensate for the uneven heating, and that's where we get our ocean and our atmospheric circulations. We need to take a look at the concept of the Coriolis effect and the concept of what's known as the three-cell model of the general circulation of the atmosphere, the breaking of the whole globe into 6 large circuits, 3 in each hemisphere, and how that affects not only the atmospheric circulations, but also the climate of the Earth. We want to take a look at storms and the different types of storms, the 2 basic large-scale types of storms we have, which would be frontal storms and then tropical cyclones. And we also want to take a look at the fact that the ocean does not boil in the tropics and freeze solid at the poles because of the circulating atmosphere and ocean that moves heat to the high latitudes. All right, and we also want to take a look at the fact that the flow of air greatly influences the movement of water in the ocean. So what we've learned is that the ocean and the atmosphere interact with one another. The atmosphere is the volume of gases, water vapor, and all airborne particulates that envelop the Earth. And the troposphere is the very lowest layer of the atmosphere in which all actual weather occurs. And it's called the troposphere because tropo means turning, because in this low level layer where all the weather occurs, you've got upward motion and downward motion both happening in the atmosphere. So weather is the atmospheric state at a specific place and time, and climate is the long-term statistical sum of weather in an area. The atmosphere is composed mainly of nitrogen, oxygen, and water vapor. Mostly nitrogen, 21% oxygen, and then a very small amount of argon, carbon dioxide, neon, helium, and methane, and then other elements and compounds. But of all of that, water vapor can make up to 4%. It can also be absolutely no water vapor, 0%. So water vapor is variable, a variable gas, making up anywhere between 0% and 4%. So what is the composition of the atmosphere? The lower atmosphere is fairly homogeneous, meaning it's mostly the same, a mixture of nitrogen, oxygen, and water vapor. The density of air, and remember, density is mass divided by unit volume. So density is the amount of stuff in the volume of stuff. So if you have the same size cube of styrofoam as the same size cube of lead, there's way more stuff in lead. It's much more tightly packed together than in styrofoam. And so the lead is much denser than the styrofoam. Styrofoam floats, lead sinks. So the density of air is influenced by temperature and water content, water vapor content. Warm and moist air is less dense and lighter than cold and dry air. Cold and dry air is more dense. It's heavier than warm and moist air. And the reason why that is when you add water vapor to air, it replaces either oxygen and nitrogen. And when you look at the atomic structure of oxygen, nitrogen, and water vapor, what we see is water vapor is actually a lighter gas than oxygen or nitrogen. So if you replace some nitrogen and oxygen with water vapor, as you would in the lower levels of the atmosphere, that more humid air is less dense. Due to changes in air pressure, meaning at the surface air pressure is highest because the entire mass of the air, the atmosphere, is above us. As you go up in the atmosphere, that mass decreases, and so the pressure decreases. So as pressure decreases as air ascends, it allows the air to cool. Due to changes in air pressure, ascending air cools as it expands. Cooler air can hold less water, so water vapor condenses into tiny droplets, and that creates clouds. Descending air warms as it compresses and the droplets evaporate. So what that means is as air rises, the drop in pressure causes the parcel to expand and the temperature of the air to cool. As it gets cooler and cooler, that colder air can hold less water vapor, so it gets to a certain point, the dew point, where the parcel is 100% saturated. Once we get to that point, further lifting or cooling actually causes condensation, meaning the water vapor turns from a gas to a liquid, tiny droplets that we see as clouds. And so rising air cools as it expands until it reaches its dew point and 100% relative humidity or saturation, and further lifting causes cloud formation. As you take that same parcel and then force it back down, as it gets lower and lower and lower, the pressure increases, more mass of the atmosphere above you. The pressure increases, that causes the parcel to compress. That causes it to warm and those droplets evaporate. So rising air creates cloud cover and sinking air creates creates evaporation or clear skies. So weather is the state of the atmosphere at a specific time and place, while climate is the long-term statistical view of the weather in an area, with rising air creating what's typically known as foul weather, clouds and possibly showers, and sinking air creating fair weather. All right, this is the type of illustration you may have seen many times since late in grade school, the heat budget of the Earth with incoming solar radiation, meaning the light coming from the sun, incoming shortwave radiation, sometimes caused as insolation, and then outgoing radiation, because the Earth absorbs all the radiation that comes in, but it also then re-emits radiation. So it absorbs the incoming shortwave radiation and then re-emits radiation in a longer wave in the form of heat. So the estimate of the heat budget of the Earth on an average day, about half of that incoming shortwave radiation of sunlight that arrives at the upper atmosphere gets to the Earth's surface. The rest of it's scattered or reflected or maybe absorbed. Then heat leaves the Earth as infrared or long-wave radiation. The Earth absorbs what shortwave radiation arrives at the surface, the Earth heats up, and then it re-radiates back out to space its heat. Now, since inputs equals outputs over long periods of time, the heat budget is balanced. So the Earth is in thermal equilibrium. Attempting to achieve that equilibrium, atmospheric circulations move heat and moisture back and forth, because at any given spot or region, it's not in that perfect equilibrium. So it's the movement of heat or moisture in attempting to achieve that equilibrium that creates our atmospheric and oceanic circulations. Equal amounts of sunlight are spread over greater surface areas near the poles than in the tropics. So look at this picture. If the Earth was straight up and down, and we know that it's tilted at an angle, but just say it's straight up and down, at the equator, the rays of the sun would strike perpendicular, meaning one ray of sunlight would have to heat up a very small area, where at the same time at the poles, that ray of sunlight would come in at less than 30 degrees, about 23, 24 degrees, and would have to heat up a much larger area. Take a flashlight, shine it straight down the table, it makes a small circle. Turn it at about a 25-degree angle, it makes a much larger circle. So there's way more insolation arriving at the surface at the equator than arriving at the poles, and so the equator is warm and the poles are cold. In addition, ice near the poles reflects a lot of that energy, so it doesn't actually warm the Earth. And at the poles, the thickness of the atmosphere is thicker. Because it's coming in at that low angle, the sunlight has to travel through a much thicker atmosphere, and that scatters more of the sunlight. In the end, much more shortwave radiation, incoming shortwave radiation, arrives at the equator than arrives at the poles. So the equator will be warmer. The Earth as a whole is in thermal equilibrium, but the different latitudes are not. Way more heat comes in at the equator than escapes, and so there's a surplus of heat at the equator, and much less heat comes in at the poles than escapes, and so there's a deficit. The average annual incoming solar radiation absorbed by the Earth is shown along with the annual infrared radiation emitted by the Earth. And again, it creates a surplus at the poles and a surplus at the equator and a deficit at the poles. So heat needs to be transferred from the equator to the poles, and that creates the general circulation of the atmosphere. The Earth trying to achieve equilibrium, transporting heat from the equator to the poles. So the ocean doesn't freeze away, and the ocean doesn't freeze at the poles, and the ocean doesn't boil away at the equator, because heat is transferred by winds and ocean currents. And ocean currents play a very large role in that heat transfer. Global circulations are driven by uneven solar heating and the Coriolis effect. Now, we're going to talk about the Coriolis effect in a minute and show you actually a couple of different videos on that. Because the water's high heat capacity, meaning water can hold a great deal of heat before it changes temperature, the ocean currents actually move great amounts of heat poleward. However, water is extremely high latent heat of evaporation, meaning it gives up a lot of heat when it condenses and absorbs a lot of heat when it evaporates, means that water vapor transferred by atmospheric circulations moves even more heat polewards. The greatest amount of heat transport happens in the atmosphere with water vapor condensing and evaporating, but the ocean does move a great deal of heat as well. So masses of moving air account for about 2/3 of the poleward movement of heat, and the ocean currents move about 1/3. All right, so what is the reason for the seasons? The seasons are caused by variations in the amount of incoming solar energy as the Earth makes its annual rotation around the sun on an axis tilted by about 23.5 degrees. So what does that mean? It's a pretty accurate view of the Earth's annual rotation around the sun. It's not quite a perfect circle. It's a little bit of an ellipse. It's pretty close to a circle, but not quite. And the axis is always 23.5 degrees from vertical. Now that axis always points in the same direction. It's pointing at the North Star, by the way, which isn't a special star. It just happens to be the star that the axis is pointing at. So whether we're in the summer, as you can see on the left, or the winter, as you can see on the right, that axis, that North Pole, is always pointing in the same direction. So in the summer, we're actually tilted toward the sun, so the northern hemisphere gets more direct sunlight, and the North Pole is always in some degree of sunlight. And in the winter, we're pointed away from the sun, and so we get much less solar insolation, and the North Pole is actually in some level of darkness the entire winter. At the spring and the autumn period, or fall, the axis is pointed to the same direction, but because we're sort of on the side of our rotation, the entire side of the globe is heated evenly. So in the springtime, at spring and fall, the first days of spring and fall, you get 12 hours of daylight and nighttime. In the summertime, you get the longer day, and in the wintertime, you get the shorter day. So during the northern hemisphere winter and southern hemispheres, winter in the southern hemisphere summer, during the northern hemisphere winter, the southern hemisphere is tilted toward the sun, and the northern hemisphere receives less light. During the northern hemisphere summer, the situation is reversed, and that's the reason for the seasons. All right, so what is a convection current? A convection forms in a room when air flows from the hot radiator back toward a cold window. So as air heats up, like all substances, it expands. If it takes up more volume, it then becomes less dense than the air around it, and it rises. Air warms, expands, becomes less dense, rises over the radiator. Air by the cold window cools, and because it cools, like all substances that get cold, it contracts. It contracts, takes up less volume, becomes more dense, and so it sinks to the floor, and that creates the convection current, where air rises, then moves toward the window, sinks to the floor, and then moves toward the radiator. So hypothetically, if our Earth did not have a tilt, it was completely smooth, let's say just covered by water, and also did not spin, it did not have any rotation whatsoever, at the equator, air would get warm, it would expand, become less dense, and rise, and at the poles, air would become cold and it would sink. And that situation would create one large convection cell in each hemisphere, north and south hemisphere, with air rising at the equator, moving north to the pole, sinking, and then traveling back down to the equator. That would move warm air north and cold air south. So a hypothetical model of Earth's air circulation if uneven solar heating were the only factor to be considered. The ideal model of the global circulation, a single cell model, develops in which air heated at the equator rises and moves poleward to then cool, sink, and return to the equator. This is not the case, as the global circulations are actually governed by uneven solar heating and the Coriolis effect, and that uneven solar heating changes because of the summer and winter, because of the tilt of the axis. All right, the Coriolis effect is the observed deflection of a moving object caused by the moving frame of reference of the spinning Earth. We'll talk more about that. How does this apply to the atmosphere? As air warms, expands, and rises at the equator and moves towards the pole, instead of traveling straight toward the pole, the air is deflected to the right, to the east. In the northern hemisphere, air turns to the right. In the southern hemisphere, air turns to the left. So this is the Coriolis effect. If you're sitting at the equator in the city of Quito, or you're sitting in the northern hemisphere in the city of Buffalo, Buffalo and Quito are on the 79th line of west longitude. They're just directly north and south from one another. Because the Earth is spinning counterclockwise as you look at it from above, in Quito you're moving toward the east. But in Quito, because of the thickness of the Earth, it's fat, it's 25,000 miles around at the equator, and it takes about 24 hours to make that trip. You're traveling almost 1,000 miles per hour to the east. You may not feel it. That's because the whole Earth is spinning and everything is spinning with it, so you don't feel it. But at Buffalo, it's a much smaller disk because you're closer to the North Pole, so you're not moving nearly as fast. In Buffalo, you're moving at about 783 miles per hour. So the speed at which you're moving in Buffalo is slower than the speed at which you're moving in Quito. If you launch anything into the atmosphere, whether it's a cannonball or a golf ball that's going to travel the entire distance, or a paper airplane or whatever it is, that object has that motion of 1,000 miles or so to the right when it leaves Quito, which means by the time it gets to where Buffalo is, to the north, it's traveled several hundred miles further, and it looks like it's actually been deflected to the right. So Buffalo travels a shorter path on the rotating Earth each day. If you look at it from above, again, the North Pole shows that Buffalo and Quito move at different velocities. One, again, close to 1,000 miles per hour, one close to about 780 miles per hour. As observed from space, a cannonball 1, shot northward, and cannonball 2 shot southward, move as we might expect. That is, they travel straight away from the cannonball and fall back to Earth. But if you observe it from the ground, cannonball 1 veers slightly to the east and cannonball 2 veers slightly to the west of their intended targets. In the northern hemisphere, the cannonball is going to be deflected to the right. The effect depends on the observer's frame of reference. If you're looking at it from space, that cannonball is going to go straight, but from the Earth, it appears to be deflected to the right.
Coriolis effect. An object in motion appears to be deflected from its course, as if a force is pulling it sideways. To demonstrate this point, let's imagine a game of catch being played by two people on a merry-go-round that spins like the Earth, but is flat. Without rotation, the ball appears to follow a straight path from thrower to catcher.
So without the merry-go-round rotating, if you throw that ball, it goes straight from one person to the other. That's the dotted line we see from above.
Imagine the ball is tossed from the center to someone at the edge. With rotation, the ball still travels in a straight line in space, but because the catcher is moving, the ball misses. From the vantage point of the catcher, the ball appears to curve away.
So again, the dotted yellow line is how you'd see it from space. It's moving in a straight direction from where it got thrown to where it was supposed to land. But from this person's vantage point and from this person's vantage point, it looks like it got deflected to the right.
The direction of apparent motion is to the right when following the path of the ball. Now the ball is thrown the other way. Because the thrower is moving, the ball has a velocity component to the right. The motion of the ball appears deflected to the right, and the ball misses the catcher again. Let's look at a throw across the merry-go-round. Both people move with the merry-go-round. The ball is thrown. Although it flies straight, it appears to be deflected from its original path. Apparent deflection increases as the ball travels farther. In the southern hemisphere, rotation is clockwise when viewed from over the pole. Again, the ball follows a straight course, but its apparent flight path is diverted. This time, the effect is to divert the motion to the left. On Earth, all free-moving objects, including masses of air, are subject to the Coriolis effect. In the northern hemisphere, objects are diverted to the right, as viewed from the direction of original movement. In the southern hemisphere, the deflection is to the left.
So this is how the Coriolis effect influences the movement of air in the atmosphere. Global air circulation is described as a 6-cell circulation model. Now, oftentimes this is referred to the 3-cell or triple cell model because really we're talking about two hemispheres, the northern hemisphere, that mirror one another. Air rises at the equator and falls at the poles, but instead of one great circuit in each hemisphere, there are 3 in each hemisphere. The influence of the Coriolis effect on the wind direction is one of the reasons for this. The circulation shown here is ideal, that is a long-term average of wind flow. So again, in a short period, it's not always exactly like this, but the equator is here, air warms, it rises, it begins to move north, and then it gets deflected to the right. All right? So as air moves and rises, In the upper levels of the atmosphere, it gets deflected to the right. Air sinks here, all right? Now, the orange arrows are what's happening at the surface. Air sinks here. So as this air sinks, it strikes the surface. It can't go into the ocean, so it moves away. As it moves away, it's deflected to the right. And as it moves away to the north, it's deflected to the right. So in this one cell, this first cell, air rises, moves north, and sinks. It sinks at about 30 degrees north latitude. Where it sinks, it strikes the Earth, and it's deflected to the right, to the south, and deflected to the right, to the north, creating these northeast trade winds, and here, the westerlies. So the westerlies, created by the motion to the right, the northeast trade winds by motion to the right. Now, the opposite happens in the southern hemisphere. So you get air rises, it moves south, it sinks, it's deflected to the left, and deflected to the left. So here you have the northeast trade winds that converge on the southeast trade winds. So just like here at the surface where winds sank, they strike the Earth, they can't go into the Earth, so they move away. Here where winds converge, they pile up. They actually are forced to rise. So not only is this rising air created by the heating, but it's also created by this convergence. Now, up at the poles, cold air sinks. It moves south. It gets deflected to the right from its vantage point of its original point, so it gets deflected to the right. And that air converges with the westerlies. So the westerlies are moving to the right. The polar easterlies are moving to the right, and they converge around 50 to 60 degrees north latitude. That also causes that air to be forced up. So at about 50 to 60 degrees north latitude, there's this thing called the polar front, where the easterlies are converging and the westerlies are converging. That forces air to rise as well. So you get this area in the 50 to 60 degree north latitude range, where you have this polar front that has cloudy and unsettled weather, just like we have cloudy and unsettled weather at the equator. So our three cells, the Hadley cell, the Ferrel cell, and the polar cell, create rising air, clouds and showers and storms at the equator, sinking air and dry weather at about 30 degrees north latitude, rising air and clouds and showers and storms at about 50 to 60 degrees north latitude, and sinking air and fair weather at the North Pole. And the opposite occurs again in the southern hemisphere. So that's what this looks like again, just a slightly different view. You have your air rising at the equator, moving north and sinking, creating the subtropical high pressure and the belt of low pressure at the equator. A belt of low pressure because air is rising, a belt of high pressure because air is sinking. And again, the high pressure sinking at the North Pole causes the easterlies to move to from the north to east, and the westerlies are moving from the south and west. So they are converging here, creating uplift and that polar front. Your three-cell model of the Hadley cell, the Ferrel cell going in the opposite direction, and the polar cell. Now, just from the standpoint of nomenclature, this is a thermally driven circulation cell because of hot air rising here. This is a thermally driven circulation cell, convection cell, because of cold air sinking here. The Ferrel cell is literally a mechanically driven circulation cell because it's with air forced up here and air being forced down here. And again, very important to understand that because air is sinking here, it creates this high pressure and a whole huge belt under the subtropical highs of fair weather and dry conditions. And at the equator, a whole huge long belt of rising air and showers and storms, and a belt of low pressure as well at the polar front and our polar high. So, three cells exist in each hemisphere, the Hadley, Ferrel, and polar cells. Wind patterns that can also be found within those cells, the doldrums, the horse latitudes, the trade winds, and the westerlies. So the doldrums are here at the equator. And the weather might be active, but they're called the doldrums because it's always the same. It's always hot and humid and stormy in the afternoons. Typically, that's when you find the storms in the hot regions. The horse latitudes is this big belt of high pressure where air is sinking, creating high pressure and fair weather and very light winds. It was given the name of horse latitudes by early seafarers. I'm talking 16, 17, 1800, because if they were on the ocean in this region, there's very little wind and their boats wouldn't move. They'd be becalmed and they couldn't get to where they wanted to go, so eventually they'd run out of food, and it's a little dicey, I hate to say it, but they basically ate horses, and so that's where they got the name the horse latitudes. And there's also the trade winds and the westerlies. So again, the trade winds are these persistent northeast winds or southeast winds in the southern hemisphere. This is how the early explorers got across the Atlantic Ocean. They sailed from Portugal south down to the northern coast of Africa, then picked up the trade winds that brought them right to where? Oh, the Bahamas, right just north of the equator and north of the Caribbean. So these trade winds were very important to early seafarers, and the way they got home is they sailed up North America and caught these westerlies and sailed back to not to New England, but to England, to the UK. The circulation in the 6-cell model is ideal, a long-term average of wind flow over the planet as a whole. Local details vary due to different surface conditions, such as the distribution of land masses, and the ocean's thermostatic effect is a major factor reducing irregularities in the cell circulation over water. All right, so what does this large-scale circulation do in terms of winds? Here's a regional. So we go from the global circulation to a regional circulation. This is the monsoon. Now, typically, if you think of monsoon, you probably think of just rain. But what a monsoon means is a seasonal reversal of winds, a seasonal reversal of winds. In the wintertime over Tibet, in this high Tibetan plateau, very, very high. And the reason why it's very, very high is because the subcontinent of India was part of a plate that moved forward and ran into Eurasia. And that continental and continental plate convergence right here caused a crumpling and uplift, which created the mountain range, the Himalaya mountain range in the Tibetan plateau. So this high elevation region in the wintertime gets very, very cold very, very, very quickly. So air sinks, creating high pressure here. As it sinks, eventually it moves across the Himalayas and then very rapidly moves downslope and gets pushed off of India and Southeast Asia into the Indian Ocean, the Bay of Bengal. And that offshore flow creates a very, very dry 6 months. And then in the summertime, as this high elevation area heats up very quickly, then rising air creates low pressure. Now the air gets pulled up the Himalayas and off the Bay of Bengal and off the South China Sea into Southeast Asia and off the Indian Ocean into India. And that onshore flow creates air that is forced upslope, cools due to pressure changes, condensation, clouds, and showers. And so in the summertime, you get your very wet period. So here's a regional circulation, smaller scale circulation, and it's forced by the change in seasons and high pressure in the wintertime and low pressure in the summertime. A local sea breeze circulation is what occurs here in Florida, and that's where during the day, if you go to the beach, let's just say you go to the beach in July, and it's the sun just came up at 7 o'clock, the ocean's about 78 degrees and the land's about 78 degrees. What is the temperature of the land at 3 o'clock in the afternoon? Well, the sand's about 1,000 degrees Kelvin, right? It's burning hot. Now, let's just say it warms very quickly to about 90 degrees because the land heats up and cools off much more quickly than the ocean. So the ocean's still at 78 degrees and the land's maybe at 90 or 92 degrees. So air rises over the land, sinks over the ocean, and as that air moves inland, it creates what's known as the sea breeze. That's what keeps the beaches cooler. And that upward motion creates clouds and showers. Because again, low pressure, rising air means foul weather, clouds and showers. And then at nighttime, the whole thing flips. The land cools off much more quickly than the ocean. Cool air descends here and air moves offshore, creating what's called a land breeze, and you get clouds offshore. Think about the last time you were ever at the Atlantic Ocean at the beach at 7 or 8 o'clock in the morning. Was there a line of clouds a few miles offshore? Well, that was that line of clouds that was created by that land breeze. All right. Storms, such as frontal storms or even tropical cyclones, are variations in large-scale atmospheric circulations. Storms are regional atmospheric disturbances, rotating masses of low pressure, either within a tropical cyclone or between two large air masses, such as in an extratropical cyclone, are storms that are regional atmospheric disturbances. Tropical cyclones originate in the tropical regions. As you know, they can create lots and lots of damage. And then those extratropical cyclones are actually frontal cyclones. They form along that polar front, that 50 to 60 degrees north latitude area where the air is rising, that front. They form along that polar front between the hemisphere's polar cell and its ferro cell. So very cold air to the north and warmer air to the south. And those frontal extratropical cyclones, sometimes also called mid-latitude cyclones, occur mainly in the winter hemisphere when temperature and density differences across the polar front are most pronounced. In the wintertime, the polar region is very, very cold. The mid-latitudes are a little bit milder, so you have a nice pronounced temperature difference. That creates those frontal storms. So tropical cyclones originate in the tropics. They are tropical depressions, tropical storms, hurricanes, okay, also sometimes called cyclones in the Indian Ocean or typhoons over in the eastern that is Western Pacific. Extratropical cyclones are storms with fronts. You have a low at the center and a cold front and a warm front. All right, so this is how those extratropical cyclones or those frontal cyclones develop, sometimes called a mid-latitude cyclone. Here's that polar front, 50 to 60 degrees north latitude, right there, with warmer air to the south and colder air to the north. Remember, the polar easterlies cause the air to come in from the north and east, and the westerlies cause this air to come in from the west. So the air is moving by each other with this sort of stationary polar front in between. Some perturbation in large-scale general atmospheric flow at some point causes some cold air to be moved to the south, perhaps some warm air to be moved to the north, and this frontal boundary gets a kink in it. At that kink where winds come together, now look at this, the winds are converging, an area of low pressure forms at the surface. So think about that red L you see on a surface weather map. That is right there, that area of low pressure forms at the surface, with cold air being pulled down behind it and warm moist air being pulled up out ahead of it, and that's what causes your cold front and your warm front to form. And of course, these move along with the upper level winds from west to east. As they move along, that cold front advances and the warm front advances, and that's what this looks like at the surface. Here's your cold air advancing at the surface. This is the same, that's the cold front there, cold front there. Warm, moist air is ahead of it, so that cold air is dense, it's more dense. So it forces that warm and moist air to rise, creating clouds, showers, and thunderstorms. Or, where the warm air is advancing to the cold air, that warm air is less dense, so it rides up and over in front of the warm front, that cold air, and it forces it to rise, creating clouds and precipitation. So in your frontal cyclone or your mid-latitude cyclone, your clouds and precipitation are going to form and develop along the cold front, where air is forced up very readily, and you get thunderstorms that develop, or clouds and precipitation will develop out ahead of the warm front, where there's a more gradual uplift, so you get light showers, and your snowfall is going to occur here in the northern sections where the air is coldest. So there is a good look at your mid-latitude cyclone with your surface low, your cold front, your warm front's probably out here somewhere, cold, dry air being pulled into a very warm air mass. So that's your extratropical cyclone, sometimes called a mid-latitude cyclone. That's where two air masses meet, cold and warm. Tropical cyclones or hurricanes. So again, tropical cyclone is the overall nomenclature, whether it's a hurricane, tropical storm, or tropical depression, or in other parts of the world, a cyclone or a typhoon. They all come under the umbrella of tropical cyclone. They occur where you have warm, humid air that's rotating. As we know, hurricanes are going to be 74 miles per hour or faster. The energy, where does the energy come from? The energy of a mid-latitude cyclone or a frontal cyclone or an extratropical cyclone, that energy comes from the difference between the cold and the warm air. When we're talking about a tropical cyclone, the energy comes from the condensation of vapor into liquid. Remember, when water vapor condenses into liquid cloud droplets, it releases tremendous amounts of energy. So the other aspect, again, with all this energy comes the wind, and with the wind comes wind blowing over the water, and water can create that storm surge. All right, so that's what our tropical cyclone looks like. Air is being pulled because our area of low pressure is at the center. Air is converging, spinning counterclockwise into the low. The uplift from that low pressure creates the uplift in these towers. Warm, moist air is lifted until it reaches its dew point or saturation. Further lifting creates condensation. Condensation releases tremendous amounts of heat. That heat causes that air to rise even more quickly. So tropical cyclones are essentially heat engines. They are vertically stacked, virtually straight up and down. And any disruption of that vertically stacked nature of the storm tends to break these storms apart. So, but when we have light winds aloft, these strong winds come to the surface. That center section, of course, is the eye. But each of these different towers, each of these different rain bands has a tremendous amount of warm, moist air rising. And you have to think about it. It comes in warm and moist. It rises. It cools due to a change in pressure as it goes up until it reaches its dew point. But once it reaches its dew point, condensation then releases a tremendous amount of additional energy. And so again, that latent heat of condensation that's released, that drives these tropical cyclones. So the dynamics, the air moves inward toward that area of low pressure. It's deflected to the right by Coriolis, and that's where you get that spinning eye of the hurricane. We'll take a look at this particular video that'll give us a better idea of that concept.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low pressure void in the middle.
So let me give you an idea of what that actually looks like on this particular graph. So she talked about high pressure on the outside and low pressure on the inside. So essentially, this is the ocean. That's my bad ocean. That's my terrible L. And so here you have high pressure on the outside. And what does that mean? With high pressure, it means the air is sinking. There's more air above the head, so air molecules are sinking. Here, air molecules are sinking. Again, as I showed you with the triple cell model, they strike the ocean. They can't go into the ocean, so the air moves away from the high pressure and toward the low pressure. And as it moves towards low pressure, that is when it's deflected to the right. So where air moves in toward low pressure at the surface, that causes air to rise. And it's where air rises that it cools as it goes up because of less pressure. It expands. As it cools to its dew point, the measure of moisture in the atmosphere. Further lifting causes cloud formation, and condensation releases more heat and showers, and even some thunderstorms. But typically you don't get a lot of thunder with tropical cyclones. So that's the way it looks like. That's what it looks like from the side. All right, let's go ahead and finish this up.
But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
So a little bit of information on frontal storms or mid-latitude cyclones, also called extratropical cyclones. That's areas of low pressure with cold fronts and warm fronts. And then a little bit of information on tropical cyclones, the tropical storm, tropical depression, hurricane, or cyclones or typhoons, as they're known in other parts of the world. And we're going to wrap up Chapter 7, again, on atmospheric circulations with just one last look at tropical cyclones and the typical tracks of tropical cyclones. So the breeding grounds of tropical cyclones always in the warm, humid areas. Now you can see, if you look at this illustration, there's a thin line right along the equator where we don't see tropical cyclones form. Between about 0 degrees north latitude and south and about 8 degrees north latitude and south, tropical cyclones don't form, literally because the Coriolis effect isn't strong enough to get the low spinning. Once you get north of about 7 or 8 degrees north latitude and south of 7 or 8 degrees south latitude, you have enough Coriolis effect to actually get this system to begin to spin. So you can see that the storms generally follow curved paths. If you think about the overall circulation of the atmosphere, the equator is what's known as the intertropical convergence zone. Okay, that's where air is rising at the surface, and then again, it's sinking at about 30 degrees north latitude, which is right about in here. As the air sinks, it creates those northwest trade winds, and then also those northeast trade winds, and then the southeast trade winds. So now in this tropical area, the winds are dominated by northeast trade winds, and south of the equator, southeast trade winds. And that tends to take hurricanes and move them along from the east to the west, which is unusual. Most weather systems across North America, across Asia and Europe, move from west to east. But because these tropical cyclones develop so far to the south, their motion is from the east to the west. Now, the reason why they have this gentle turning to the right is because of Coriolis. Also, once they get far enough north, about 30, 35 degrees north latitude, then those westerly winds become an issue, and that tends to deflect those storms back off to the east. So the best track for any tropical cyclone in the Atlantic Ocean is to form way out here between Africa and South America and slowly turn to the right, get far enough to the north of the equator that Coriolis becomes more pronounced, and then the westerlies pick it up and turn it off toward the North Atlantic. Then the tropical cyclone does its job. It moves heat and moisture to the north, but we don't have any landfall, we don't have any storm surge, and we don't have any damage from winds and flooding. So the breeding grounds of tropical cyclones are shown in orange shaded areas. The storms follow those curving paths. First they move westward with the trade winds, east to west. Then they either die over land or they recurve north and then eastward until they lose power over cooler waters of the mid-latitude. Remember, if tropical cyclones are powered by the latent heat released from warm and humid air, if a tropical cyclone moves over land or moves over colder water, it loses its fuel. Cyclones are not spawned in the South Atlantic or the Southeast Pacific because their waters are too chilly, nor in the doldrums within a few degrees of the equator. And again, that's because of the lack of Coriolis. All right, that wraps up Chapter 7, Introduction to Oceanography. In Chapter 8, we're going to continue to talk about circulations, but now we're going to talk about ocean circulations. We'll be taking a look at ocean currents, how they are driven, what creates them, and how they move around the globe, and what that means ultimately to our climate.